Hi everybody, this video is to help you better understand osmosis. So to get started, first let's go back to diffusion. Diffusion is the movement of particles. So solutes that are dissolved can diffuse from one side to another through a selectively permeable membrane as long as they can pass through. They always move from high to low. So if you look at this diagram, it is showing that we have some molecules over here. Here they're in very low concentration, and here they're in higher concentration. And if they were going to diffuse, we would actually just move some of these actual solutes across. That would be diffusion. In this picture, you see that water has moved. So we're going to talk about how sometimes this membrane here is selectively permeable and it won't allow certain solutes to move. If the solutes can move, that's diffusion. All right, we're going to move into osmosis. Osmosis is when water is moving. Again, it's also going to move from high to low. So where there's an area with a lot of water, it'll move to an area that has less water. You can think of it two ways. You can think of it in terms of the water, or you can think of it in terms of the solute concentration. But the important thing is you're always doing a comparison of two solutions. If you talk about tonicity, that means are things hypertonic, hypotonic. I'm sure you remember those words, but we're going to go over them today. You're going to talk about the ability of water to move back and forth. Usually before you talk about the water moving, you talk about the osmolarity. And osmolarity just gives you a value for any solutes that are in a solution. So you can compare osmolarity, and you use the same types of prefixes if it's hyperosmotic or hypoosmotic. You're talking about how many solutes there are comparatively in one solution versus another. All right, so first let's talk about hypertonic. I'm going to draw a beaker here, and in this beaker I have a solution and I have a cell in here. So if I talk about the solution being hypertonic, this solution must have more solutes in it than my cell. So I could go around and I could put a lot of solutes, and let's say this is salt water. So here are all the salt particles within my beaker. Inside the cell, there is a lower concentration of salt particles. So inside the cell would be hypotonic, and outside of here, it would be hypertonic. You always want to compare, so obviously if the solution's hyper, then the cell must be hypo. All right, next one, hypotonic. So this time, I draw my beaker, I have my solution in it, I draw my cell, and this time if my solution is hypotonic, then my cell is hypertonic. So I want to draw more particles inside my cell, showing that the solute concentration is higher inside the cell than outside of the cell. All right, so now I want to spend some time talking about what moves. Now that you know that we have two different solutions, let's talk about the way in which they move. We're going to assume that whatever these solutes are, they cannot cross the membrane. So the only thing that we're going to have moving is water. So I want you to imagine water moving. Water would move into this cell. So I'm going to draw a bunch of arrows of water moving in. And I'm going to write H2O is moving in. Now I could also have some very small arrows going out, but the overall flow is the net movement of water going in is greater than the net movement of water going out. And if this is an animal cell, there's a good chance it's going to swell and possibly even burst. All right, I want to go back for a minute. Oh, it's not letting me go back. All right, let me draw the cell that we had in the last solution for a second. This solution is hypertonic. So remember, it had a lot of particles around, and my cell was hypotonic. In this situation, water would move out of the cell, so my cell would shrink. And again, I could do a couple arrows because the net movement, there is going to be movement in both directions, but there's going to be a lot more water exiting the cell. So water always moves from an area of hypotonic to an area of hypertonic. So I love to tell this little story right here to help you remember it. Think of the word hypotonic. So picture the O in hypotonic. That is a kid with a big fat water balloon. And think of hyper. When you think of hyper, you think of a kid that's had too much sugar. So a hypertonic solution is the one that's very concentrated, has a lot of sugar particles in it. And the O has a lot of water. Well, if there's a kid with a big water balloon and there's another kid who's hyper, what's going to happen? It's going to throw the water balloon at him. So water always goes from the hypotonic solution to the hyper. All right, hopefully that story helps you remember. All right, isotonic. So in this diagram, here's my beaker, here's my solution. I have an equal amount of solutes in and outside. So the overall net movement is equal. The arrows are going in and out, and there's a relatively equal amount of water moving in and moving out. So the cell's going to stay around the same size. This again was that reminder, water is always going from the O, think of the big fat water balloon, to the hyper solution. So the kid that has had too much sugar is going to get hit with water, and that is going to happen until the solutions are isotonic. Or it's at least going to try and get that way. All right, solving YouTube problems. So I'm going to draw a little YouTube for you. This, oh, I don't like that one little bit. I'm going to use my eraser. Okay, let me try again. Sorry, I am writing with my finger here. Okay, this is my selectively permeable membrane, and let's say I have this glass tube. We'll call this side A and this side B. And they both have water in it right up to the same level. And then I'm going to put some particles in it. So I'm just going to put these little dots, and these dots are going to represent glucose. So let's see. I have 1, 2, 3, 4, 5, 6, 7, 8. So I'm going to write over here, I've got 8 glucose on this side. And then over here on this side, let's make 4 of them. 1, 2, 3, 4. All right, so I got 4 glucose on this side. Now, I also want to make some other stuff. So let me see if I can change my pen here. 1, 2, 3. I'm going to make 3 starch on this side, and I'm going to make 1, 2, 3 starch on this side. I am randomly assigning these numbers. I am not like planning it out. I'm just trying to make a little solution here. All right, so questions often ask you to compare these solutions at the start. So at the start, the first thing you want to do is actually just add up the solutes. This is our osmolarity. So 8 plus 3, I've got 11 solutes on this side. Now again, that's such a rough made up number. I'm just counting the number of solutes over here. It's not like a perfect, like, oh, it's a 5 molar solution and a 3 molar solution. So this is actually how you have to just go through and solve some of them, is to just use them like they are a molarity. And over here on this side, I have 4 and 3, so I have 7. So right now, side A has more solutes. So side A right now is hypertonic because it has more solutes, and side B right now is hypotonic. All right, next thing I want to talk about this membrane. Let's say this membrane is permeable to the glucose, but impermeable to starch. And that makes a lot of sense, right? Because glucose is a monosaccharide, starch is a polysaccharide, so chances are it might be permeable to glucose, and chances are it won't be permeable to starch. So now we got to think about moving things. So I have 8 glucose here and 4 here. So the easiest thing to do, and obviously this one's pretty easy to solve, but you can add the 2 numbers together. So 8 and 4 give me 12. I want to divide it evenly between 2 sides. So I'm going to bring it to 6 on both sides. So I cross this out and put 6, and I cross this out and put 6. So what has happened is some of my little glucose is moving over. So I'm going to label that G. So my glucose is moving over from side A to side B. Now, what you need to do next is you need to cross off these numbers and re-add. So 6 and 3, I now have 9 on this side, 6 and 3, oh my goodness, I have an isotonic solution. All right, so obviously I just made up these numbers because now I'm not moving water in either direction. The next thing I would do is see about moving the water. But if I end up iso and iso, my water levels are going to stay the same. All right, so then the amount of water going to this direction and going to this direction would be equal. All right, let's try another one. Let's make up another problem here. So here's my YouTube, and here's my membrane. And let's give myself some particles. I'm going to call this side A and this side B. And let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All right, I got 12 glucose over on this side. 1, 2, 3, 4. I have 4 glucose over on this side. And let's go ahead and put 10 starch on this side. So I'm going to change it and make these be another color. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And let's put, 5 of them over here. 1, 2, 3, 4, 5. 5 starch. Okay, so here I am at the beginning. My starches are my blues, and the reds are my glucose. And this membrane is going to be permeable to glucose, but not to starch. So at the beginning, first thing I need to do is compare the solutes. So I add this up, and I've got 17 solutes here, and I have 14 here. So right now, A is hypertonic, and B is hypotonic at the start. All right, next thing I want to do is figure out what's going to move. The only one that can move is the glucose. So I add together 12 and 4. That gives me 16. Divided by 2, it's going to have 8 on each side when I'm done. So I'm going to have some of these red glucose move across. All right, I now re-add. 8 and 5 is 13, 8 and 10 is 18. Wow, now this side has now become hypertonic. So I can cross that off. It's no longer hypo. This one is no longer hyper. This one is now hypotonic. All right, my very last thing to move is water. And remember, water always moves from the O. Picture that like a big fat water balloon. So I am going to move water across. So I'm going to take this purple and I'm going to show this is going to be the net movement of H2O. My water level is going to go down on this side and it's going to go up on the B side. So my ending water values might be like that. All right, and so that's how you go ahead and solve a YouTube problem. You can go back. I have plenty of examples. You can do a lot for practice to make sure you know how to solve those. All right, now I just have some pictures that I wanted to show you. So I wanted to talk about real cells and how real cells behave. So first of all, this is an animal cell. This is actually a red blood cell that you see here. And in this first picture, here's my red blood cell. And look at these arrows. We've got pretty much equal sized arrows going in and out. So that is telling us that this solution and this cell are isotonic. If they're isotonic, we got the same amount of water moving in and out of the cell. I'm not moving my solutes, I'm just talking about water now. All right, this one. I have a lot of arrows going in, and you know, I'd have to have a tiny little arrow going out because solutions are in constant motion and some is going to go out. But the overall net movement is water going into this cell. That tells me that the solution out here is hypotonic and that my cell is hypertonic. So I want you to think about this for a second. If this is a red blood cell, imagine that you were in a hospital and you got an IV. When you get an IV, you actually get an IV that is salt water and it's in perfect concentration, isotonic with your blood plasma. That way your blood cells do not swell or burst or shrink. If instead you were given an IV of pure water, it would be hypotonic and it would cause your cells to swell and potentially even burst. Right, so we don't want that to happen. So that's why IVs are actually made in a very specific concentration. They do not give you pure water, or it would be it would kill you. All right, let's look over here at this last one. My overall net movement is for water going out of my cell. You can tell right away that this is very concentrated. This is going to be my hypertonic solution, and my cell was hypotonic, causing it to lose water. This cell has shrunk in size. Right? So that's how an animal cell behaves in an isotonic, a hypotonic, or a hypertonic solution. Now let's look at a plant. A plant has something that our animal cells do not have. Our plants have cell walls. And the cell walls, you'll remember from the biochemistry unit, they are made up of cellulose, and they're fibers, and they're pretty rigid, so they only allow the cell size to stretch a very little bit. They really have a hard time exploding. So it's actually very, very ideal for plants to be in a hypotonic solution, because a hypotonic solution adds more and more water to the cell and helps this vacuole fill up with water. When a vacuole fills up with water, it actually maintains the cell size, and it pushes against the edges, and it creates what we call turgor pressure. I'm going to put TP here for turgor pressure. That keeps a cell upright. If you think about a plant wilting for a minute, when a plant wilts, the cells have actually lost water, and the cell walls start to cave in on itself, and the overall plant loses its structure. There are no bones, there are just cells with cell walls around it. If the cell walls cave in, the plant wilts. So ideal for a plant cell is to be in a hypotonic solution, because it will bring in water, and that water will push against the edges of the cell wall, and it will not burst. The cell wall usually does not break unless there's like a freezing. If there's a freezing of a cell wall, it's more likely to break, but under normal conditions, hypotonic is ideal. Whereas in an animal cell, it was the isotonic that was ideal. Here's isotonic, here in the middle. We've got an equal amount of water going in and water going out. And it's not ideal. See these little gaps right here? It's showing that the membrane of the cell is not pushing against the cell wall. So it starts to become what's called flaccid. And when it's flaccid, it's just not enough pressure. There's not enough turgor pressure, and a plant is going to begin to wilt. All right, here we have a cell that is undergoing plasmolysis. So let me write that down. Plasmolysis is horrible for a cell. This cell has lost a lot of water. So the solution has got to be hypertonic, and my cell was hypotonic, and the water has gone out. The cell has shrunk, and the next thing that's going to happen are these walls are going to start caving in, and the cell is going to die, but then also the overall plant is going to wilt and die because the cell walls are going to cave in. All right, so that's what it looks like in a plant cell. All right, I really liked this slide. So this is my last slide, and it's just a great review. So this is a great thing that you can add to your notes. I very much encourage you after this video to go back and for your Cornell notes, go look up different solutions, and you will find different problems to solve. So you can go ahead and practice some more YouTube problems. But then you can also find great images and add the images to your notes. They'll help you understand it more. So here we have an animal cell, a plant cell, and we're putting them in different solutions. So first off, you'll notice the solution that the cells are being placed in is hypotonic. So that means the solution they are in has very little concentration of solutes and a lot of water. So water ends up going into this cell, and lyse means that it bursts. It's pretty great for a plant cell. It's pretty ideal because, again, it's going to increase that turgor pressure. All right, now we go over to the isotonic one. The isotonic one, it's not so great for the plant cell. It starts to actually cave in a little bit, but it's awesome. So I'm going to put a little star by the ones that are ideal. So it's awesome for a blood cell because you want an equal amount of water entering and leaving. All right, last we're looking at a hypertonic solution. So the solution actually had a lot of solutes, and your cell was hypotonic, so it lost a lot of water. Shrivels up. It's not ideal in either situation, not for animals or plants. Now if you go down here, characteristics of the solution compared to the inside of the cell. The solution, if it's hypotonic, has a lot of water and not a lot of solutes. That means it's low osmolarity, meaning there's not a lot of particles in the outer solution. And the pressure is low, meaning that there isn't a lot of pressure because there aren't a lot of particles. Then if you go over here to our one that is hypertonic, there is, I'm sorry, this one's isotonic. It's equal on the two sides. So this is sort of our like dull and boring, which is great for an animal cell, but it just means you've got equal concentrations of solute inside and outside the cell. All right, and now let's go over to our solution that was hypertonic. If the solution is hypertonic, it does not have much water, but it has a lot of solutes comparatively. That means high osmolarity. That means there's a lot of particles. Osmolarity, again, was when you counted up the particles. And then the pressure is high because all of these particles show that it is about to receive a lot of water. So that causes that increase in pressure. All right, let me know if you have questions and do some practice.